started, which is good. All right. Record is on, and we are moving on to a new topic, okay? Because we are done with binary comparison, if I remember correctly, or we are not. We haven't talked about binary comparison in this class. Yeah, I think we may not because I just turn on the video. I know we talked about two's complement, so that's what today's lab is. And that's coming from a signed versus unsigned integer representation or interpretation. So what we'll do today is we are moving on to binary comparison. Okay, so we'll be comparing numbers, but in base 2. All right, so with that said, I am going to get started with, um, oh, okay, it stopped working. That's okay, we got it. All right, oh, there you go. Okay, so what we'll do is we are going to start with binary comparison today. So binary comparison is about in a subtraction, how can we tell that x is less than y? That really is the question. Okay, so we are going to take a look at a few scenarios. So I'm going to work out the binary subtraction here, and then we look at the result of the binary subtraction, and then go like, what? How do we know, whether x is less than y? So we'll start with easy stuff first. Okay, so we have basically 2 minus a say 4. Okay, so this is 2 minus 4, and we'll do the actual binary subtraction. This is x, y, q, t, and then the d. All right, we put a 0 here. And then the q is the exclusive or between the x and the y. So we have 0, 1, 1, 0 here. And then the t depends on the previous column. So this particular t depends on 0 minus 0 has a borrow of 0, or 0 minus 0 has a borrow of 0. 0 or 0 is just a 0. And then this particular borrow here is dependent on 1 minus 0 has a borrow of 0. 1 minus 0 has a borrow of 0. 0 or 0 is also a 0 here. This one depends on 0 minus 1 has a borrow of 1. 1 minus 0 has a borrow of 0. 1 or 0 is a 1. And then this one is based on 0 minus 0 has a borrow of 0. 0 minus 1 has a borrow of 1. So now we have 0 or 1, which is a 1. Okay. And then finally, the D row is the exclusive or between the Q and the T. So now we have 0, 1, 1, 1. Okay. So do we have any questions about the binary subtraction itself? Because the way I figure out all these individual digits is to use the binary or the logical operations. I did not rely on arithmetic operations. Okay, but that part, even that part, is a little bit irrelevant at this point. The question is, if I look at 0010, okay, the VU of 00104 is a 2. The VU of 0100 of 4 is a 4. So 2 minus 4 is supposed to be a negative 2, but we have a 14 here. So we have a result of 14, but we also have a borrow. The borrow looks like a 1, but because it is on digit 4, so that means the actual amount that we are borrowing is a 16. So that means you have $14 in your pocket, but you owe the bank $16. Your net worth is negative 2. So we actually got our negative back, our negative 2 back, except it is not expressed as a negative number. It really is a negative number too. So if you look at the VS of 1110, it is actually negative 2. So let me just kind of throw that out here too. So the VU of 1110, 4-bit, that is 14, but the VS of 1110, 4, is a negative 2. All right. So right away, I'm using notations that we talked about in the previous class, which is VU, VS. So do you guys remember what they represent? Hmm? Okay. So VU is the unsigned interpretation of a bit pattern, and then VS is the signed interpretation of a bit pattern. Okay, and the equations, there are formulae already expressed in the form of a sigma notation. So that's coming from the previous class, okay, when we talked about signed versus unsigned representation. So that's not even the focus of today's class, okay? In today's class, our biggest question is x less than y? And if so, how do we know it? Yep, because 1110 is a 14 because we have a 2 plus a 4 plus an 8. So that gives us a 14. So 14 is also the unsigned interpretation of 1110. The 16 is coming from here. This is the borrow because it's a bit 4. So that means we have 1 of 2 to the power of 4. That's a 16. Yep. Because the position of the bit tells you is 1 of what. The unit is based on the position. Okay, all right. So what we want to know is whether x is less than y. But that is a really obscure question because now in this particular example, you may think, oh, how is that possibly confusing? Because x is 2, y is 4. We're really asking whether 2 is less than 4, which is true. So later on we'll use some examples. But in this case, x is less than y is actually true. Okay, so we'll take a look at, how we can tell that is the case. All right, another example. So this time it is a little bit more confusing because this time we have 1110 minus, we'll throw in 0001 just so that it's not terribly difficult to do. So this time I'm not going to spell out the actual binary subtraction. So we'll just kind of do it quickly. 1111 over here. There's a 1, and there will be 000, and then we have 1. Let's see. That should be a 1, and then the 0, 1, 1. Yeah, that looks about right. But now the question is, if I just ask you whether x is less than y, then you should probably come back and say, attack, this is ambiguous. Because when I look up that number wheel thing with 16 numbers in it, 1110 has two interpretations. In the signed interpretation, it is -2, which we covered in the previous slide. In the unsigned interpretation, it is 14. So whether 14 is less than 1 is different from whether -2 is less than 1. Because 0001 only has one interpretation. Because both the signed interpretation and the unsigned interpretation come back as just one. So that one cannot be confusing. So y cannot be confusing, but x can be confusing because 1110 has two interpretations. So now what I just wrote here really is not a good way to do it because what I should have asked is whether VU of x4 is less than VU of y4 and also whether VS of x4 is less than VS of y4 because in this example, they come back to be different values. Are we doing okay so far? All right. So we'll focus on one thing at a time, okay? So we'll focus on just the VU because, the VU is the easier one. So in this case, this is false, okay? This is false. In the previous case, it is true. So when you look at this one, okay, and then you look at this one here, of all the bits that are already computed, do you see one particular bit where if it is a 0, it means x is not less than y, and if it is 1, then x is less than y. It is conclusive. You can go like, oh, yep, we can just look at that one bit, and then we can tell whether x is less than y. Which one is it? Hmm? Say again? Digit 3 of who? Well, but that way, but what if they have the same sign? Right. So I need one single digit of all the things that are already computed here that can tell me conclusively whether VUX4 is less than VUY4. Yep, the borrow that is hanging out, right? Yep, you're correct. So in this case, T of 4, okay, which is this bit here, this bit is a 1 if and only if VUX4 is less than VUY4. Okay. All right, so with that conclusion, let me go back to the notes here because I do want to kind of bring this up so you guys know, where you need to study in order to get all these conclusions. So this one has to do with binary comparison, which is this particular link here. And then once you get there, it has some highlighting. So the green boxes was my attempt to tell my students which part of this module is really important and do not skim over that part. The rest is kind of like, yeah, if you skim over, it's not going to be the end of the world, but what is inside the green boxes should not be skimmed over. So in this case, okay, this is what I just said a little bit a few minutes ago. In a binary subtraction of two m-bit patterns, in this case, in our example, m equals to 4, um, Tm is a 1 if and only if Vu, the unsigned interpretation of x up to m bits, is less than Vu, which is the unsigned interpretation of y up to m bits, assuming T0 is a 0. So that is in a green box, which means this is not the part that you can skim over. All right. So that seems, okay, it kind of makes sense, right? Because what is T, T of m in this case? It's a borrow bit. When do you need to borrow? When x is less than y. Okay, but only in the unsigned interpretation. So the signed interpretation is hmm, a little bit interesting. So we'll go back and look at some more examples, but those are all pertaining to the signed interpretation. So section 3.1, you can see it is a long mathematical thing, and it is not inside the green box, which means if you want to skim over, you can go ahead and skim over, especially if you have not taken CISP 440 and you don't understand what is proof by induction, then just kind of skip it over, okay? Skip section 3.1 if you do not know what is proof by induction. On the other hand, if you have taken CISP 440 and you know what is proof by induction, you might want to read through section 3.1 just so that you understand another application of the technique that we call proof by induction. All right. So now we go back to the example. Okay, we go back to Supernote, and now we look at some kind of really interesting cases. Okay, so let me go to another one. Okay, so another page. And this time I have, say, 1001 minus 0100. Okay, and some of you, especially you looked at the sign, right? So right away we know this is x, this is y, by the way. So right away we actually know that the sign interpretation of x has to be less than the signed interpretation of y. We don't even need to carry out the entire calculation. And why is that? Okay, since you mentioned bit 3, why is bit 3 important when we are looking at the comparison of two signed interpretations? Well, it has to do with how VS is defined. Okay, so how is VS defined in this case? By the way, what is VS X4? How do we calculate that? We add up a bunch of powers of 2, right? Except for one that we subtract from the rest. So in this case, the 1 means we have 1 of 1, 0 of 2, 0 of 4, add them all together, it's just 1. Cool. But this one over here, which is supposed to be 1 of 8, we do not add, we subtract that from the sum of the other powers of 2. So now we have these 3 bits add up to 1. This bit here specifies let's subtract 8 from it. So that means the sign interpretation of 1001 is actually negative 7. Okay. What about the other one? Well, the other one is fairly straightforward. So we add up none of 1, none of 2, 1 of 4, which is all 4, minus none of negative 8. Oh, okay. That really is just 4. So that is correct. Yep. The most significant bit, which is bit 3 here, is indicating if it is a 1, it means the value represented or the signed interpretation is negative. If it is a 0, then the signed interpretation is guaranteed to be non-negative. All right. But we're going to carry out the calculation anyway. So we have Q, T, and then the D, and we just go for the entire thing. So this is just exclusive OR, no borrow here, no borrow here. There's a borrow here, and then no borrow over here. And 1, 0, 1, and then a 0. Okay. So we'll do a quick sanity check and see whether it makes sense or not. This is basically 9 in decimal. This is a 4 in decimal. This is a 5 in decimal. Okay, everything seems to work out. But when you look at this one, they go like, but how can we possibly tell that Vs x is less than Vs y? Okay, there's no pattern in this case. All right. So in theory, what can we use to indicate the result of signed comparison? So, section 4 talks about signed comparison. So we start off with just, normal algebra stuff, okay? So that means, if we can confirm that x is less than y, if x is less than y, okay, if x is less than y, if and only if x minus y is less than 0, okay? So let's look at this claim here. Does that make sense to you? This is basically saying x is less than y if and only if x minus y, the whole thing, is less than 0. Does that make sense? X and y being integers. They can go positive or negative. Yes? Okay. So x minus y is our d because that's what d stands for. It is the difference. So that means if d is negative, then d of m minus 1, m is the total number of bits, and d of m minus 1 is the most significant bit, it should be a 0. Okay, so let me just go over this again, okay, this chain of reasoning. Using algebra, we can say, okay, x is less than y if and only if the difference of x and y is less than 0. That's just algebra. But if the difference is less than 0, that means d of m minus 1, which is that's also called the sign bit or the most significant bit of d, the difference, has to be a 1 based on what we just talked about, right? So that means, oh, okay, so we can just use d of m minus 1, which is the most significant bit of the difference, to tell whether x is less than y from the signed interpretation. Yep, yes. So example, the second example does not play by that rule, but the first one does. hmm That is correct. It works for all cases. Okay. So this would be, you are correct. So this is 1 plus 2, none of the 4, but we also have to subtract the 8 because of the most significant bit. So that means this bit pattern is can be interpreted signed as negative what 5. The power of 2 corresponding to the most significant bit is subtracted instead of added. Yep. And that was that was actually mentioned in signed versus unsigned representation. So I really want to point out where we talk about these things, because it's actually at the very end of this entire discussion. That's how VU and VS are defined. So you can see how VU just add up everything, right? All the powers of 2 corresponding to every position of X, they are just added. But when it comes to the sign interpretation, it's sort of like that, except we leave out the most significant bit. You can see how in the sigma, this one ends with W minus 1, this one ends with W minus 2. So what are we going to do with bit W minus 1? It specifies whether we should subtract the power of 2 corresponding to that position. So that's echoing what you just mentioned, your observation. Right. Yep. Right. That is correct. Now, but that still does not, yeah, yes, but it still doesn't really answer the question of can we have all ones, over here, and it will overpower the most significant digit or the power of 2 corresponding to the most power, it, can the rest of the bits add up to a certain amount so that it is actually greater than the power of 2 specified by the most significant digit of a base 2 number? The answer is no. Okay, because let's say you have 4 bits, okay, and it is 1 1 1 1. 1 plus 2 plus 4 is only a 7. So they can, even combined, they cannot overpower the 8, which is digit 3. Okay, sort of, yes. Sort of. But in this case, it has to do with the individual digits, cannot add up to, even if you add up all the lower digits, they cannot add up to the same amount. Yep. So so the answer is 8 is not one of the numbers that can be represented when you only have 4 bits and you choose to interpret signed. Hmm. So when you have, all right, so if you look at 1111, okay, so the VS of 1111, and you interpret all 4 bits, will be 1 plus 2 plus 4. Those would correspond to the least significant 3 bits, but then you'll still be subtracting an 8, so it's negative 1. Okay, so let's check out the definition first. Yep, it is 15. Because in the unsigned interpretation, you just add up all the powers of 2. You cannot. You cannot. Because each bit combination for each interpretation, there can only be one interpretation. So when you look at the bit pattern of 1111, Then you out if you say, okay, what is the unsigned interpretation? It's 15. What is the signed interpretation? It's -1. But once you have chosen the interpretation, there's only one value that you can interpret it as. 15 cannot be represented using only 4 bits. Yep. If you need to represent it, yes. Yep. That is correct. All right. So now that we got that cleared up, is this making sense now? Because if x is signed, y is signed, then x is less than y if and only if the difference between those two is less than 0. In other words, using algebra, I just decide to subtract y from both sides. You subtract y from x, you get x minus y. You subtract y from y, you get a 0. Is that making any sense? Okay. But by definition, d is the difference, and it is x minus y. So that means if d is less than 0, then based on what we just observed earlier, like 2 minutes ago, then the most significant bit of d, because m specifies the total number of bits, so d subscript of m minus 1 is the most significant bit of d. So if d is less than 0, then d of m minus 1 has to be a 1. So that means we should be able to use d subscript m minus 1 to indicate after a subtraction whether x is less than y, interpreted signed. Okay, but I use the word should, which means it doesn't work all the time, which is also what the super note is illustrating right here. Because in this case, we know for sure that xs of x4 is less than vs of y4, because -7 is less than 4. But yet at the same time, d subscript m minus 1 is a 0. So now we go like, what is going on here? Because the previous examples, they all work. Because in this case, we go like, okay, vsx4 is less than vsy4. And in this case, d subscript m minus 1 is a 1. So it does work out. And we look at another case here, okay, even this one. So in this case, we also say vs x4 is less than vs y4. But in this case, you can see that d subscript m minus 1 is also a 1. So it works in this case, it works in this case, but it doesn't work in this case. So why is it not working? Well, it's not working because what is the actual value of -7 minus 4? So without thinking about binary numbers, what is -7 minus 4? -11, right? -11. So you look at that number wheel, and can someone tell me whether -11 can be represented when you only have 4 bits? The answer is no, you cannot, right? Because -8 is as negative as you can possibly be. So -11 is out of range, which is also called overflow. So what we are now learning is if the result of a subtraction is out of the range of the number of bits that you're given with, then the sign bit of the difference no longer tell you whether x is less than y. It is telling you the opposite. Is that okay? This is what I really like the most about this class is we're only talking about addition and subtraction, and then somehow the discussion goes like, what are we talking about? This is not even calculus, right? This is like we are just adding and subtracting, okay? What happens when you subtract a positive amount from a negative amount? It should be negative, but yet this is not negative. This is 5. It's like, what is going on here? Because we ran out of bits. Okay, we simply do not have enough bits to represent -11. Okay, it's called overflow. So now we have a few things. Okay, so let me continue to use super note here. Okay, so we made a few observations. Okay, the first observation is if there is no overflow, d subscript m minus 1, which is the sign bit of the difference, is a 1 if and only if vsxm is less than vsym. So that part we have established, okay, because that's just algebra. If x minus y is negative, the sign bit of the difference should be a 1. Okay, cool. Except when it is out of range. Okay, so now the question is, how can we detect this overflow? So on the next statement, we say if there is overflow, then it is opposite. D subscript m minus 1 is a 0 if and only if vsxm is less than vsym. So it sounds like what we need to do now is to say, how can we tell whether there's an overflow or not, right? So let's go back to the previous example, and you guys can tell me what is the easiest way to tell that, yep, we got an overflow. So we're looking at this specific example here. What is the quickest and easiest way to say, tag, we got an overflow, because that does not make sense. What does not make sense to you? Mm, no, doesn't. The borrow flag or the borrow flag is not part of our consideration at all. Okay, so I'm gonna put these in a rectangle, and then you tell me what does not make sense about these three bits or the way they combine. How are they not making sense? Okay, so apparently we have someone who has figured that out. So a negative amount minus a positive or non-negative amount ends up with a non-negative amount. Okay, so if you have made that observation, congratulations, because you just applied what we talked about today in right almost right away. You're basically reusing what we have just been talking about. Because in this case, this one here tells me that x is negative. Now, how negative? I don't even care. Okay, it is negative. This 0 here tells me y is, or the signed interpretation of y is non-negative. Now, how positive it is, I don't care, okay? This 0 here is telling me the difference in signed interpretation is non-negative. So just by looking at the sign of the minuend, the subtrahend, and the difference, they do not make sense. That is how we know we have an overflow situation. So let me just kind of pause here to make sure everybody understand the reasoning behind this particular observation. Are we all good with that observation? All right. So you might say, but Tech, there has to be another way this does not make sense. Because the other way that this is not going to make sense, let me kind of give you the actual concrete example here, is something that looks like this. Okay. So let's say you have let's say a 5, okay, and then you decide to subtract mm, -4 from it, okay, so -4 is this bit pattern here, okay, so we'll just go ahead and do all the actual calculation, but I'm not going to spell it out, okay, so exclusive OR, this is 1 0 0 1, and then there's no borrow here, there's no borrow here, there's no borrow here, but there's a borrow here. And then finally, we get 1 0 0 1. So I don't trust my actual calculation, so I'm going to go do a sanity check here. So looking at the unsigned interpretation, this is 5. Looking at the unsigned interpretation, this is 12. So 5 minus 12 is -7. Okay, so now we look at this, it's like, but tag, this is this is 9 using the unsigned interpretation, but we have a borrow of 16. So 9 minus 16 is still a negative 7. So I just perform a quick sanity check to make sure that I did not mess up the calculation. But this time, the signs also do not make sense. Because what do we have here? This time we have a non-negative quantity minus a negative quantity ending up with a negative quantity. That also does not make sense. Is that all right? So there are two cases that do not make sense. All other cases actually can happen, okay? Some has to happen, some can happen. So we'll go ahead and take a look at all the cases here. So we are looking at x of m minus 1, which is the sign bit of x, y subscript of m minus 1, which is the sign bit of y, and also the sign bit of the difference after the bitwise operation. This is a truth table, okay? So we have 8 entries in this case, because we can say, oh, what if all of these bits are independent to each other, which is not really the case, but we'll pretend that they are not. So these are the 8 possible cases. And now we ask, do we have an overflow? So with the first row, we're asking if you subtract a non-negative quantity from a non-negative quantity, can you end up with non-negative quantity? Yeah, pretty sure that can happen. 2 minus 1 is a 1. Okay, all right, so there's no overflow here. If you subtract a non-negative quantity from a non-negative quantity, but ending up with a negative quantity, can that happen? Easy. 0 minus 1 is a negative 1. Okay, it can happen, so it's not overflow. What about this one here? 0, 1, 0. So we start off with a non-negative quantity. We subtract from it a negative quantity, ending up with a non-negative difference. Can it happen? Well, not only can it happen, that's what it should happen. Okay, so there's no overflow here. This one we just saw, it is an overflow. This one we saw also, it is an overflow. What about this one? This one has to happen because you are subtracting. Whoops, I take it back. Sorry. It has to happen so it's not an overflow. Because in this case, we are subtracting a non-negative quantity from a negative quantity ending up with a negative quantity. It makes sense. This is the only one that makes sense when you have xy being like this. With the other two, I'm just going to kind of fast track it and say that they all make sense. So this particular truth table only has 2 rows that are ones, meaning that only those 2 particular rows correspond to an overflow situation. So we want to go like, okay, so if we know that this is the truth table for overflow, what is the formula? What is the Boolean expression to make this happen? So the way we work on that is to ask, how can we come up with this one over here? How can we come up with an expression that is a 1, but only for this particular row? Well, in that case, we can negate x subscript m minus 1. And when I use what looks like multiplication, it is conjunction. So we're ANDing it with y of m minus 1, and then ANDing that with d subscript m minus 1. So when you look at not x m minus 1 and y m minus 1 and d m minus 1, that conjunction is true only for this row here. For all the other rows, it has to be a 0. Does that make sense? We good? All right. So now we look at the next row. You go like, oh, okay, but using the same trick, this one means we have x subscript m minus 1 and the negation of y subscript m minus 1 and the negation of d subscript m minus 1. Because in this case, we need to keep x subscript m minus 1 as is because it is a 1 to begin with. But we need to negate y subscript m minus 1 because it is a false to begin with. We need to turn it into a true so that the conjunction becomes a true. The same thing goes for d subscript m minus 1. So these two, one would make the fourth row a 1, one would make the fifth row a 1, but they will all be false for all of the other rows. So that means now we can conclude that overflow can now be expressed as the negation of x subscript m minus 1 and y subscript m minus 1 and d subscript m minus 1, or the other one, which is x subscript m minus 1 and not y subscript m minus 1 and not d subscript m minus 1. M minus 1 simply means it's a sign flag. This is the sign bit of that component in the subtraction. So are we good so far? Okay, so we now have a way to figure out whether there's an overflow situation or not. But that's not the answer that we are looking for. It is a part of the answer that we're looking for, because ultimately we want to know whether x is less than y. Okay, overflow is something that we need in order to figure out whether x is less than y. So now we need another truth table. So the next truth table is saying, okay, there's d subscript m minus 1, and now we have overflow. And now we want to come to the conclusion, is v as x m less than v as y m. So now we have another truth table, but this one is easier because we only got 4 possible cases. So 0, 0, 0, 1, 1, 0, and then 0, 0. I hope you guys still remember. Whoops, sorry, I take it back. These two should be both ones. Sorry, that was my bad. There we go, 1, 1. All right, so if you remember what we said a little bit earlier, when there's no overflow, the sign bit of D tells me whether the sign interpretation of x is less than the sign interpretation of y already. So that takes care of this row and also this row, because hey, if there's no overflow, we can trust D subscript m minus 1. So those two are done. Nope, take it back. Because we can trust D subscript m minus 1, so the third row has to be a 1. Is that okay? So what did we say about overflow? If there's an overflow, then the sign bit of the difference tells you the opposite of whether x is less than y. So that means, hey, for this one, since we see a 0 here, we have to flip that 0 to a 1. For this row, because there's an overflow, if the sign bit says x is less than y, then we flip it around and go like, nope, that is not the case. Okay, so are we okay with how the truth table is constructed based on the interpretation of what is the sign bit of the difference and also the overflow flag, which is really just saying, hey, can we trust the sign flag? If the overflow is a 1, it means we cannot trust the sign flag of the difference. And if the overflow is a 0, it means yes, we can trust the sign bit of the difference. But if you ignore, okay, if you just ignore the top portion, which is the heading of the table, if you just kind of cross this out, what does it look like to you? Exclusive OR, okay? So that means now we can define the L flag, L for less than, okay? It's really just, oh, okay, so it is the sign flag overflow with, um, exclusive OR with the overflow flag. The sign flag is just another name of D subscript m minus 1, which is the sign bit of the difference. We good so far? Question? Nope. Okay. hmm So this is signed comparison, okay? And you can write down the notes, and I would highly suggest you to put all the definitions to one place so it's easier for you to look it up. But everything is actually in here as well. So when you look at the signed, this is signed versus unsigned, which is the previous one. So when you look at this one, there's a whole bunch of stuff that is not in a green circle. Hey, look at this. This is how we define the overflow. And also look at this one here. This is the L flag. It is the sign flag of the difference, exclusive or with the overflow flag. And that's it. That's the essence of this particular reading module. Okay, it tells us what we can look at after a binary subtraction so that we can tell whether the signed or the unsigned interpretation of y is less than the same interpretation. Well, excuse me, I take it back. Whether the signed versus the unsigned interpretation of x is less than the same interpretation of y. There we go. Are there any questions? Do you guys want me to kind of give you guys more examples? Let's do some more examples. All right, so I'll let you guys tell me which two 4-bit number you want to subtract, and then we'll work out, all of those bits. So just give me the two things that we want to subtract. Okay, what is x and what is y? Give me 4-bit numbers. 1100. Okay, there we go. All right. So the thing is, can we tell right away which way it's going to be? Okay. So, um, so one way you can do this is really to quickly ask what is VS X4 and what is VS Y4. Okay, we'll start with X. What is the signed interpretation of the bit pattern X up to 4 bits? It's 5, right? Because it's 1 plus none of 2 plus 1 of 4, and then we do not subtract an 8 because the bit corresponding to the 8 is a 0. Okay, so that's, yes, it is a 5. What about the signed interpretation of y? None of 1, none of 2, 1 of 4, but we also subtract an 8 from it. So this is negative 4. So I already know this is going to be an overflow because 5 minus negative 4 is 9, and 9 cannot be represented using the signed interpretation using only 4 bits. Because the range of a signed 4-bit pattern is negative 8 to positive 7. 9 is not within that range. So I can tell right away there's an overflow, which also means the sign of the difference is going to lie. It's going to tell us that, oh yeah, 5 is less than negative 4, but it's wrong because there's an overflow here. So I already know what's going to happen. But now let's go ahead and to carry out the actual subtraction. In other words, I use another way to interpret what we are dealing with here to come up with the answer right away. Okay, there's an overflow, the L flag should be a 0, and the sign flag of the difference is going to be negative in this case, or it's going to be a 1 because we are going to end up with a mistakenly negative signed interpretation of the difference. Okay, but now we're going to work out all the bits. So we got T, and then D over here. This is going to be 0. All right, so exclusive OR. Okay, this is 1 0 0 1. And now there's no borrow, no borrow, no borrow, one borrow here, and it becomes just 1 0 0 1. Okay, sanity check. This is a 5, this is a 12. 5 minus 12 is negative 7. This is a 9, but since we have a borrow of 16, we also end up with a quantity of negative 7. So everything works out. So now we say, okay, what about overflow? Well, in this case, overflow. Okay, so let's spell out the whole equation. D subs. Oh, no, I take it back. X subscript m minus 1, negation y subscript m minus 1, negation d subscript m minus 1, or the negation of x subscript m minus 1 and y subscript m minus 1 and d subscript n minus 1. So now we throw all the bits in, okay? This is a 0, this is a 1, this is a 1, this is a 0, this is a 1 and a 1. But since we're negating, this becomes a 0. Since we're negating, this is 0. On the other side, the 0 is negated into a 1. These two are not negated. So that means this entire side gives us a 0 for the conjunction. This entire side gives us a 1 for the conjunction. So now the disjunction as a whole is going to be a 1. We do have an overflow situation. Okay. So when you combine that with this is the sign flag here, this is the actual sign flag. So the L flag is the sign flag exclusive OR with the overflow flag, which in this case is a 1 exclusive OR with this one over here. One exclusive OR with one is a 0. So since the L flag is a 0, so the conclusion is the signed interpretation of X is not less than the signed interpretation of Y, which is correct. Are we good? Then what about the unsigned interpretation? Because we might as well talk about the unsigned interpretation too. So in this case, what is VUX4? I mean, if you guys can figure out what is VS, VU is actually easier because everything is just added, right? So what is VUX4? It's also 5. What about VUY4? It's not 5, it's 12. That is correct. So in this case, can someone remind me again, what flag tells me whether the unsigned interpretation has X being less than Y? Which flag should we look at? Or which 0 or 1 should we look at? The borrow, the overall borrow, right? This guy here. Okay, very good. Yep. So in this case, T of 4 is a 1, but that matches the fact that VUX4 is less than VUY4. So it is consistent. Are we good so far? Yes. All right. So who could have imagined that just adding and subtracting and just zeros and powers of 2 can be this confusing? Yes. Yep. Well, this is complicated partially because I use a lot of symbols. Okay. So T of 4 is a symbol. What does it mean? Okay. Well, you kind of have to remember the definition. Okay. What is the T row representing in a binary subtraction, right? So a lot of this has to do with understanding the symbols. Okay. Which is something that nobody is born with. So it is all from studying. Hmm? Yep. All right. Any questions about this? Yes. Okay, so let's go ahead and do that. Okay, tell me again which two numbers? 0100. Okay. Okay, very good question. Why do we have an overflow here? So we can look at that from two perspectives. One is to look at V as x4. This is x, this is y. And that would be what? -7. That is correct. And then what about V as y4? That is correct. So when we look at Vs x4 minus Vs y4 and just go for straight subtraction, we end up with 11, correct? But we also know that 11 is not in the range of a 4-bit signed number because a 4-bit signed number can only go from -8 to positive 7. 11 is out of that range. So from that perspective, just from looking at the range of a 4-bit signed number, we know that we have an overflow already. Is that okay? So now we can look at the actual. Okay. So now but are we good with the interpretation based on really just the sign interpretation and how the sign interpretation is out of range? So we get that. Yes. Go ahead. Hmm? Oh, it's negative 11. You're correct. It is negative 11, which is also out of range because it goes from negative 8 to positive 7. So negative 11, but you're correct. I forgot about the negation. Okay, so now we look at this from the actual mechanical subtraction and see what happens here. So we got Q, T, and then the D. So 1101, no borrow, no borrow. Yep, we have borrow, no borrow here. And another row of exclusive ORs, 101, and then a 0. So once again, I want to do a sanity check. This is a 9, this is a 4, this is a 5, with no borrow from the unsigned subtraction, so that works out. But to answer your question, this sign does not make sense because you are starting out with a negative quantity and you are subtracting a non-negative quantity from it, and you end up with a non-negative quantity. So from the bitwise operation perspective, this also tells you that we have an overflow. Correct. That's the core reason why we have an overflow, but the actual mechanism also shows you that something does not make sense, which is the sign of the overflow. Well, I shouldn't say sign because sign is meaningful in this class. It is a indication that we have an overflow. Yes. Yep. 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 So we can go back to the definition of the overflow flag. So x subscript n minus one is a one from here. This is a zero. This is a zero. But since we have a negation, the zero turns into a one. Since we have a negation, that turns into a one. So now we have a conjunction of one, 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 which means the whole thing is a one. This is an OR, so that means the entire disjunction is going to give us an OR. So mechanically speaking, the overflow flag is going to be a 1 based on how we compute it using the digits. So there are two, as you said, there are two perspectives. One is the semantics, which is basically based on, okay, how are we interpreting the bit patterns? And if we are to perform a normal subtraction, what is the quantity of the difference? Is that quantity within the range of values that we can actually represent in 4 bits? Nope. Okay. So that's one. But mechanically speaking, we can also just look at the conjunction of of this expression and the conjunction of this particular expression and go like, oh, but that also tells us that we have an overflow. Yep. Yep. Hmm. Right, because from our perspective, all we really care is x less than y in the sign interpretation, so that I can either not branch or branch, continue with the next iteration of the loop or whatnot, right? So that's what we really want to do is to say, oh, is this loop going to go for another iteration or not? Based on whether x is less than y. That's why we care. But the computer cannot really just say, oh, yes, it is less than or it is not less than. All it knows is to do, oh, I know how to do subtraction in binary. That's all I know. Using logic gates, okay, and translating everything down to transistors at some point. That's what the computer says, okay? I know how to do subtraction, and I'm proud of myself knowing how to do subtraction in base 2, okay? You go like, yeah, but I need you to give me the indication of whether x is less than y. The machine goes like, well, if you're talking about unsigned interpretation, that's pretty easy. Okay, T of 4 is going to tell you whether this unsigned interpretation of x is less than the unsigned interpretation of y or not. But once you move on to the signed interpretation, then we have a problem. Because normally you can just depend on the sign flag of the difference based on algebra. Okay, it's like, hey, if x minus y is less than 0, then the most significant bit of d should be a 1. But the only problem is you cannot represent every value in the integer line. You have a range of numbers that you can represent. So if that difference is out of that range, then the most significant bit or the sign flag of the difference is going to lie to you. It will tell you the opposite of what it really should have been. So that's why we need the overflow flag to tell us whether we have an overflow situation or not, and then use the truth table that we just looked at before, which is, I think, the slide right before this. And then we have to rely on this truth table to say, oh, in order to know whether this less than is happening or not, we need to look at both of these flags because they both contribute to the correct answer. So are we doing okay so far? Kind of looking at the reason why we are kind of diving into this and looking at all of these bits. Okay, all right. Let me ask you this question. What does it mean when I use the word understand? In other words, when I ask you, are we understanding all of this stuff here? What am I really asking? Okay, I'll give you a few choices and you can tell me whether that is what I'm asking or not. Am I asking whether you can regurgitate what I just said? Nope. Am I asking you whether you can find where you can find all this stuff in my notes? Nope. What am I really asking? Whether you see the connections or not. Okay, whether you see the connections. Okay, because understanding or meanings. Okay, what is the word meaning? Okay, what is the meaning of meaning? Okay, so we can throw some words out there and then we go like, okay, well, do we understand the meaning of that word? Okay, so I can always throw something that is not English. Okay, so all of you go like, nope, we don't understand what it is. Okay, so let me throw one up on the screen. Okay, right here is fine. Okay, what does this mean? You go like bunch of strokes. Okay, horizontal and vertical. Okay, that's about all you can see. Well, to me, it has meaning. It means the quantity of 5. So I have the association of seeing these strokes arranged in this particular way to the abstract concept of a quantity, okay, which is the number of fingers that you're seeing here. It's the connection. It's the association of, oh, this is associated with that symbol that you're seeing here. So when I ask you about the understanding of the concepts, such as the overflow flag or the L flag and so on and so forth, I'm asking, do you see the connections? Not only the definition, but also the connection between the definitions. Yes, go ahead. Correct. That's the implementation of the overflow flag. Yep. Hmm. Yep. So, but that also goes back to how the notes are arranged. Now, this may or may not be of importance to certain people of this class, and I'm not going to argue whether it's important or not. So you go like, well, so tech, this means that you could have just not mentioned anything outside of the green boxes, and this entire module would be very short. The answer is yes, absolutely. But if I did that, then you would not have the connections between all the symbols and understand why the overflow flag can be defined this way, or why the L flag is defined this way, or why the T of M alone can tell you whether the unsigned interpretation of X is less than the unsigned interpretation of Y. So you would have missed all the whys, even though you know the what it is. Okay? Because there are always three questions that I encourage people to ask. The first one is what is it? Okay? What does it do? Well, the L flag tells us whether X is less than Y in the signed interpretation. That's what it is. And then the second question is, why do we know that? Well, because in a loop, sometimes you have to exit the loop or stay in the loop depending on whether one side of the comparison is less than the other side of the comparison. That is why. The text that is not in the green boxes is telling you how it gets the job done. So those are the three questions. Okay. What is it? In other words, how do I use this thing? Okay. If I don't understand it's a black box, at least I have to understand under what circumstances do I use this black box? Okay, and what is it going to do for me? Why is, well, I guess it's part of what I just said. Okay, because why is, okay, why do I need this black box here? Okay, and then the how is to say, oh, I don't want to see this as a black box. I want to see what is in the box that makes it tick, that makes it work. And in some cases, how to make my own box. That is correct. So I had the opportunity, I'm just kind of relate this discussion to a conversation that I had over the weekend with somebody who is a team leader for VSP. If you don't know what is VSP, it is a local employer, VSP in Sacramento. So VSP Vision is originally just an insurance company for vision, for optometrists and stuff like that. So if you have, I cannot remember who of you, I think it was you. Your mom works for the state, so you probably have VSP coverage. So that means that every year you can go to an optometrist, have your eyes checked out, and if you need glasses, they will pay a certain portion of your eyeglasses. Okay, so that's what VSP is about. Okay, they manage insurance policies. Well, that's what they did originally. Now they also own actual optometrist offices and also companies that make eyeglasses. So they're expanding their business. So the person that I talked to works for the IT, not the IT, but the software development team of this particular company. And I specifically asked that person, how much do you use AI, to do your work? Well, as it turns out, it is a very important thing because what used to take about 6 months using AI, it shrinks the timeline to 2 to 3 weeks. Okay. Now, there's always a downside to everything because right now, the entire industry, if you look at software development and software engineering as an entire industry, everything is based on efficiency. In other words, how quickly can you crank out a code to do blah? Okay. They don't ask about, but is that code maintainable? They don't care. Am I designing an architecture so that in the future, if you just want to add some more feature, it would only take me like 2 or 3 minutes, or do we need another 2 weeks to get that new feature done? They don't ask those questions. It's all about immediate, quote unquote, immediate efficiency. Hmm? It's not about gratification, it's about money. It's about, do we really need a whole team of 200 developers, or can we cut that down to 50 people and let go of 150 people out of a team of 200? So the entire industry is thinking in that particular mode, except for the state. If you get into the state and you have a job, that's almost golden, okay, with very few exceptions. So, how is this discussion related to what we are talking about? Because we are just talking about a bunch of zeros and ones and additions and subtractions and a whole bunch of symbols, right? So how are they related? I will ask this question. Even with VSP, which is not a really big or well-known employer, okay, how many of you knew about VSP before today? None of you, right? Okay, one of you. Okay. So you knew about VSP, but because it's a Sacramento company and we are in Sacramento right now, you go like, well, maybe it's because of the locality, right? So it's not because it's like a nationwide company that's well known like IBM or Microsoft or anything like that. Can anyone imagine the number of applications they get for every software engineer position? 50,000, 50,000 applications. Hmm? Within the time frame of the job advertisement, which is usually about 2 weeks to four. 50,000 applications, 50. It used to be 5,000-ish, okay? Like a few years ago, before the AI stuff, it used to be about 5,000-ish, which is still a pretty big number. But 50,000 is a huge number. The entire Davis has a population of around 50,000 people. That kind of gives you the scale of things, right? So, what do you do after you graduate with a bachelor's degree in computer science? Hmm? Say again? Say that again? Yep. So even for a relatively small company, they're not really small anymore because they are now international. So they are extending their market to Canada and also, overseas. So they have factories of eyeglasses overseas that they're also managing. So they're expanding really quickly. But nonetheless, they're still not a gigantic employer. They're not, well known internationally. So what do you think employers look for now? Well, okay, let me rephrase that question. How much of what you learn in college, independent of the class, is directly applicable to your job application? It's almost 0%. Okay? Because especially with this VSP, job application, do you think they use C++? No. They don't. They have certain parts of COBOL, but they're using other languages, and to the point where the language itself is not really that important because you just tell the AI, okay, I need this. This is the specification of what I need, and then the AI goes cranks out the code. So, what becomes important? Adaptability, because there's no telling what you actually need to know by the time you graduate. I don't know. Most people do not know, okay, because there may be languages that has not been invented yet, okay, and And where AI will be by the time you graduate from with a bachelor's degree, I don't know either. You don't know. I don't know. Nobody knows. Okay. Sam Altman does not know. Okay. So adaptability is really the key. You have to keep learning new things and be adaptive. Um, I just read, oh, right, this is the CTO. No, this is the head researcher for Google's AI team, DeepMind. He said the most valuable skills from your perspective, people who are about to graduate in a few years, the most useful skill set is learning how to learn. It is not about what you learn in a class. It is about learning how to learn. And he said that becomes the most valuable skill because you have to learn new things. Okay. Nothing I teach here, and you guys go like, yeah, but that's because you teach assembly language, and that's because you teach this class in a certain way that makes that material useless. Nope, it doesn't matter. It really does not matter. Okay. Nothing you learn on your way to get your bachelor's degree is going to be very much directly applicable to your job application. So that means you are going to have to learn what you need to learn at the time that you graduate in order to be successful to apply for a job. Is that okay? All right. But what does it have anything to do with what we just talked about today? Since Tech, you just said that that's useless. So what is the whole point of this class? What is the whole point of going to college anymore? Learning how to learn exactly. And and from today's discussion, what are you getting out of it? How do you learn how to learn? Practice, okay? Yep. Going down the rabbit hole. Okay, that usually has a negative connotation, which is implying that, oh, you're wasting your time because you don't have to go down the rabbit hole. That is not true anymore. Okay, because the practice of going down the rabbit hole is training your mind of how to learn new things quickly. And that is what you need to do. So I hope I put everything into a certain context that is relatable to what you will be encountering. Because as much as I want your future, along with my own children's future, to be nice and easy, get your bachelor's degree, and there will be a job paying, $200,000 a year waiting for you. As much as I want that to be the truth, it is not. I cannot tell you everything is going to be rosy and rainbowy and stuff like that when it is not the case. Okay? So I know I'm using a little bit of the class time, but I think if this gets used to start to think about what I just talked about, it's already good. All right, so we are going to go back and talk about two's complement in today's lab. So we'll go ahead and publish this. And the access key is just negative. Okay, so I'll write it on the whiteboard. Negative. There we go. And I'm gonna stop the recorder. So all that stuff that was not directly related to this class was also recorded.